seconds ago, but you can start from the beginning if you want of this slide.
Okay, sorry about that. So I was talking about a question that is asked by a mathematician. Can one hear the shape of a drum? So we know that shape of a drum determines how it sounds. For example, this is high frequency, middle frequency, and low frequency sounds coming from respectively from a smaller, medium radius, and large radius drums. So this is not surprising, but actually he asks the question in a mathematically rigorous sense. So what he asked is basically, are there different shapes having the identical sound? Like in order to give an identical sound, they need to share the same spectra. So this is basically a mathematical problem. So it is the Dirichlet problem for the Laplacian. Let's say we have a domain, omega. So basically, this is also equivalent to Helmholtz wave equation. Remember, sound, this membrane is vibrating, so waves in play here. And these boundaries, they need to vanish at these boundaries, these waves. So this is the Dirichlet boundary condition. This problem is basically equivalent to asking whether the eigenspectra of different shapes can be the same. This question has been answered as, can one hear the shape of a drum question has answered as no. There are, people have discovered that there are domains which are isospectral, which means for example, these two domains, their shapes are different, as you can see, but their eigenvalues are exactly the same. And this is not just the lower, I am just showing you this lower eigenvalues, but the whole spectrum actually is exactly the same. So there are isospectral domains, which means if you prepare a drum head based on these shapes, you can tell which one is which from just hearing the sound from them. Okay, so this was about hearing the shapes, an introduction. So let's talk about quantum wells. What are they? So I will talk about quantum confinement, which is basically saying that at nanoscale, at quantum scales, the material properties can be different due to the size effects and due to the wave nature of the particles, which are very apparent at that scales. In macro world, we don't see wave nature of particles. We can treat them as point particles, for example. Let's say we have a large material and we have electrons in there. It is a good approximation for their energy levels to treat them continuous, treat them as point particles. But this is not a good approximation at nanoscale because the wave actually, electrons or the particles that you are interested in, they can feel the boundaries of the domains. And this change their wave functions and also their energy levels. So basically, from the energy spectrum perspective, this continuous spectrum is basically an approximation. In reality, it's quantum, but it is a good approximation at macro world, but it fails, of course, at nano world. And size effects, in addition to the bulk properties of the material, size effects emerge due to this discreteness of the spectrum and the fact that spectrum doesn't start from zero. Okay, so another way of looking this is basically the importance of ground state and low-lying states become prominent with reduced size. And as you can see, for example, this is the thermal distribution of these states. Just to give an example, so the smaller size, there are more states populated at the ground state and low-lying states compared to a larger size. And this is on the right, you see how a gas at thermal equilibrium looks like in these different domains. So the upper one is the smaller size and the lower one is the larger size. So these quantum wells are have been used in nanoscience and nanotechnology a lot, basically constituting the backbone of these technologies. It's basically relying on that you're sandwiching your material into some other materials, which serves as barriers to the electrons inside this sandwich material. So for the electrons confined in this gallium arsenide, their energy levels basically very similar to particle in a box energy levels. Like here there's a finite potential, but for low energy eigenvalues, it's like they cannot penetrate. So there are many applications of this, but I just want to describe you what's a quantum well. Okay, the third thing in the title is size invariance. So what do we mean by size invariance? First of all, I would like you to think about this question while I'm talking in the next slides. Can we change the shape of an object without changing its size? So think about this for a moment. But of course, in order to answer this question, we need to describe what is size and what is shape. Okay, what is size? So it is much easy compared to shape because it is defined by Lebesgue measure in mathematics, and which is basically sizes are described by these 4 parameters if you're in 3 dimensions, which we are living in. And these parameters are basically volume, surface area of an object, peripheral length, and number of vertices. So here you can see how it breaks down in a cube. And these are basically this volume in 3 dimensions is the bulk variable, and others are lower dimensional size variables. Okay, so these, if you know the values of these parameters, you know the size of your domain. But shape is kind of much more vague to define. So there is one definition which I like about shape, but there can be some others. So shape is defined as the geometric information that is imposed by the enclosed boundaries and invariant under translation, rotation, and uniform scaling. Okay, even from how it sounds, this sentence, you can tell that this doesn't tell much. It tells something, okay, like it doesn't change under uniform scaling, for example. If you enlarge your system, shape should be preserved, but it doesn't tell much. For example, so these shapes are different from each other, right? We can all agree on that. But what about their sizes? So you can make their volumes equal to each other by playing around with the other variables, but you cannot make all the size variables the same for these objects. They should differ because of the different boundaries. So what we're asking again, the question was, can we separate this size and shape effects from each other? And can we continuously change the shape of an object without changing any of these variables?
Can I ask a question before you go?
Yes.
To the next slide. So how do you define size? What is your definition of size? Because size? Like Lebesgue measure for points, I know what it is. It is just 0. So right. So like for instance, what is the size of a sphere for you? Because you cannot decompose it into flat panels, so to say, like right. Lines, surfaces, cubic volumes, and so on and so forth.
Exactly. So this was maybe this example might have confused you. So this is you don't need to break down like this for other objects. For example, for sphere, you don't have this number of vertices. These are basically, for example, this number of vertices are the discontinuity points in your system. Since there is no discontinuity in sphere, you don't have it. But you know the volume of the sphere, right? You know the surface area. And again, you don't have peripheral lengths. So yeah, this geometric size variables basically define and you don't have to have all of them in your system.
Of course, I understand that, but now I got your answer, I think. So I will let you speak, but thanks.
Thanks. So my proposition is size-invariant shape transformation, which is an extremely simple technique. So let's take a closed domain, like square here, and remove a part from inside. I just removed a square, but it doesn't have to be self-similar. You can remove some other shape. And let's perform a rotation on the inner shape that you remove. So let's compare this end result. This was the initial configuration on the left, and this is the final configuration on the right. So you can tell by eye the shapes are different, right? Shapes of the system. By system, I mean this blue thing enclosed by the boundaries. But we didn't touch any of the sizes, right? If you're looking carefully, we preserved, okay, this is 2 dimensions, so we don't have volume. We preserved the surface area. We didn't change the peripheries, and we didn't add any corners or other points into the system. So they all stay constant under this transformation. And here, in this particular case, shape transformation is characterized by the rotation angle. And as you can see, we have in our hands a method can change the shape without changing any of the size variables. So you don't need to do rotation into the inner square. You could do also translation. This is another way in 2 dimensions, and in higher dimensions, you will have additional translation, no degree of freedoms. But I will focus on rotation today. Okay, so let's connect things together. So we were talking about hearing the shapes. So we understand that hearing the shape is basically examining the spectra. So spectra determines how it determines the frequencies, right? So if you look at here, I just give you these are the eigenfunctions for the wave equation that I solved for this particular domain at 0-degree configuration on the left and 45-degree configuration on the right. And as you can see, the ground state, the first eigenvalue, is radically different from each other. So remember, we were saying volume, surface area, periphery, and number of vertices are the prime factors in determining the size, and a size directly determines the spectrum. But here, size doesn't change. By just changing the shape, we encountered with a huge variation in the ground state and also some other states. So eigenspectral, okay, this is different from isospectral domains, right? Remember, isospectral domains had the same spectra. Here we have a different spectra, but we have the same sizes. And I just, for fun, to make an analogy, I promised you that we will hear the shapes. So I just take this difference and normalize into an octave. And this is, I started the initial reference point as A4, and this is how it sounds. This is a flute. And as you can see, this is, by the way, ground state. I didn't add the overtones. And this is reduced to G4. As you can see, it's a lower sound, and this is because the ground state is lowered. Okay, so at this point, I would like to mention a very important conjecture put forward by Hermann Weyl. So in 1911, he was studying this kind of systems.
Can I ask one thing before we proceed?
Yes, Tekin Hocam.
I think the example you had given, the genus is one. You have carved out just a single portion. You can carve out 2 portions, 3 portions, higher genus. So that does make a difference as well. Are you going to restrict your transformations depending on the genus?
Yeah, for this slides, for this presentation, yes, I will. But in principle, you could make this hole smaller and just
And have many holes.
Open many holes in your system.
And that are not necessarily of the same shape or size.
But the point is, you need to make, so let's remember how we generated the size difference. So in the initial case, I opened a hole. So this is the initial configuration. So I could make this much smaller, and I could make many of them.
Yeah.
And then perform rotation to all of them or some of them at least. So
okay.
I'm not allowed to open different holes under this shape transformation because that will change my geometric size variables. That could in principle change area or peripheries and so on.
Okay. Okay.
Thanks. Okay, so topologically, these are also the same in that sense. Yes, they have only one holes. Okay, let me describe you what Weyl conjecture is. It's basically about the asymptotic behavior of eigenvalues of any shape under Dirichlet boundary conditions. This is for Laplacian, but in principle you can have different operators. I will focus on this Weyl conjecture today because it is the relevant one. So Weyl conjecture says that this is the number of eigenvalues up to eigenvalue lambda. This is how it is defined. So this is an asymptotic formula. It is true in the infinite eigenvalue limit, but it gives quite accurate results even for like low-lying states, as you will see. But notice this important thing. Under size-invariant shape transformation, we don't change the size variables. And remember, this is the two-dimensional version of this Weyl formula. These are size variables: surface area, periphery, and number of vertices. And this lambda was the eigenvalues. So the Weyl conjecture cannot differentiate these two shapes from each other because their size variables are the same. And you can see that if you plot the eigenvalues of this two different shapes, 0 and 45, which are basically this black and blue curves respectively. And this is the number of eigenvalues in the x-axis. And you will see that Weyl basically predicts this, as you can tell from here, predicts the behavior very well. It passes right from the center of this curve, but of course it fails to differentiate the shapes from each other. But this is important. I'm mentioning this because I looked at the spectral characteristics of the system under this transformation. So here on the right, you see the lower part of the eigenvalue spectrum. And you see that once you rotate your inner core shape from 0 to 45 degree, there is a huge reduction in the first eigenvalues. And it is not surprising that it is degenerate, by the way, because you can see that there are fourfold degeneracy forming in this rotation process. But as you can see, there is a huge gap that this ground state lowers hugely. And also you can see that degeneracies are broken. This is the reverse way. If you go from 45 to 0 degree configuration, you see that there is levels are splitting from each other and breaking of degeneracy. So these two characteristic behaviors in the spectra under this size-invariant shape transformation I will show you that they're very crucial in determining the behaviors. So this is an ongoing study right now I'm doing. So I want to understand how these ground state reduction occur in this system, as well as level splitting. I tried several things. I will just quickly mention this. This is very interesting that basically I found two measures for this shape variation, which predicts the ground state reduction. So on the left, you see the solid curve is the first eigenvalue changing from 0 to 45 degrees, and it is normalized to 1. And I'm proposing two measures. This one, the dashed one, is basically the inverse radius of the inscribed circle. What is inscribed circle? It is the maximum circle that is that fits to any part of the domain that you have. So here you can see this red circle basically fits to here, but its radius is increased once you go from 0 to 45 degrees. And this is quite related with the behavior of the first eigenvalue, because consider yourself as a first eigenfunction. You will try to find the most less confined place in the domain to sit, because you are you need to correspond to the lowest eigenvalue, right? So this is basically opening of some local deconfinement in the system. So this is kind of a measure of that. And as you can see, it predicts very well the behavior. It doesn't have to be like matched very accurately. That was not the purpose. And also there's another measure which is called Hausdorff distance, which is about how two shapes are similar to each other. So since this circularness of the domain is very important, and this has connections to the isoperimetric inequalities, where there is also there's a result in mathematics which relates this isoperimetric inequality to the eigenvalue spectrum. So there are connections between there, and this is kind of a manifestation of these connections in this size-invariant shape transformation. So Hausdorff measure also predicts very well this behavior. So this was important to understand how this ground state reduction can be justified in the system. Okay, so far we were talking about more from acoustic side of the things.
Can I ask one more thing?
Yes, of course.
Well, again, in your example, you want this transformation to be such that you don't want the shape to be non-simply connected, right? The shape you are showing us is simply connected, and after you rotate this carved out portion, it remains simply connected. It doesn't go doubly connected or multiply connected.
Sorry, can you remind me
the portion that you carved out, right? If it is too large, if you rotate it,
right. So
there should be some natural limit to the portion that you are carving out.
Right. I didn't mention that, but of course you shouldn't tore your domain apart.
That's what I'm asking.
Exactly. It needs to be connected, because in the end, I'm talking about a single domain, not many domains. So I'm talking about the shape of a single domain. That's right.
Thank you. And also, can I ask this factor of a quarter, minus a quarter, does it have anything to do with the fact that you are using a square?
Oh, that's true. It depends on the shape that you use. It depends on the size of the shape that you use. For example, if you make this removed square much more smaller, you will see that the difference will be less.
Okay. So if you are using a polygon,
yes,
an hexagon, a pentagon, is it going to be a fifth, sixth, etc.?
Oh, that's interesting. I didn't check that, but I have checked that in my thesis for triangle.
Okay.
But that's a good question. My intuition is it won't be like that, because it might not be that intimately connected to the number of sides you have, because in the end, this is kind of more about how this reduces this ground state. It's more about what the shape of the system in terms of, okay, what also the size of this system, like how large its area and so on. So I'm not expecting that, but it's worth to check. Thanks.
Okay. And then you are also using regular shapes, right? You are not using a rectangle, you are using a square.
But that's not a, I mean, you can use any shape.
Okay,
Yeah.
okay, thank you, thank you.
Thank you. Okay, so now I will transition from acoustic to quantum case. So in this Dirichlet's problem, which is the essence of what we're doing here, there's this analogy, there is this equivalence. After all, this is basically a domain which is fixed at ends. You can think of it as an oscillating string or oscillating wave function, which has to end at the ends. So this is equivalent. So right now I'm transitioning into not hearing the shapes, but filling this shape with some particles and calculating some properties of these particles. Okay, for example, this is just to give you an example how it can be done. Like this is basically a square, a material with a square lattice, and you can think of this system as the red sides are the leads, and where the thin white part is your domain that you're calculating the particles' properties. This is just to give you some like intuition how it could look like. So I will use statistical thermodynamic framework. You could go much more much quantum mechanically relevant things, but here I will just focus on this and show you that even at equilibrium, there are things which we don't expect can occur. So I will, for simplicity, assuming that my particles that I filled the domain with, they are obeying Maxwell-Boltzmann statistics. You could do any statistics in principle, it doesn't matter, but for simplicity, I'm using Maxwell-Boltzmann, and this is single particle partition function. For n particle non-interacting particles, partition function is written like this. This is thermal occupation probability, and based on this, you can calculate the thermodynamic properties like free energy, entropy, and internal energy. As I said, you don't need to use Boltzmann statistics. We have done calculations for other statistics as well. Of course, in order to do statistics, you need to satisfy some conditions. I'm not mentioning them here, but I want to ensure you that we are, of course, considering those things. Okay, so I'm showing you on the right how thermodynamic properties behave, how they change with the shape parameter, which is characterized by theta. So the first one is the partition function. So partition function, classically, it is a function of volume. It's directly proportional to volume. Or in 2D, the bulk parameter is area. But remember, area, periphery, they were all constant in our case. So before doing these calculations, you might expect partition function to be constant. But remember, the spectra changed, and you can see that how spectra actually affects the thermodynamic properties. So the partition function increases with the theta. So this is effectively mean that the 45-degree configuration is effectively less confined than the 0-degree configuration. So it's like if you can define effective volume, which we have defined, but I won't go into the detail of that, the effective volume of the system or area here will be increased. So this is okay, but there are more interesting things. So free energy, these are, by the way, normalized values, normalized to KT. So free energy decreases. So what free energy tells us is the direction of the spontaneous thermodynamic transition. So which means if you prepare your system in any degree configuration, like here, for example, like 15-degree configuration, it will spontaneously transition into the 45-degree configuration, which is the minimum free energy case. So internal energy is also decreasing. These can be understood again from the effective area concept. But the most interesting thing is entropy is also decreasing. This you shouldn't expect, because let's consider we have a gas in a domain, and we are looking to the free expansion of this gas, which means it's increasing its volume. So how thermodynamic properties will behave? Partition function will be increasing linearly. Free energy will be decreased because this is the gas wants to expand. And internal energy will also be decreased because the gas is less confined. What happens to entropy is entropy will be increased because now in the larger box, you have more states available for your states available for your system to be represented. So entropy must increase in this case. This is the classical picture. Something weird going on in our system, and entropy behaves differently from the other three. And this has very important consequences I will mention in a second. But before, let's focus on what is the consequence of free energy decrease. It's basically, since we have a rotation and free energy decreases, this means there is a torque that rotates the system. So I'm claiming this inner object will rotate. As you can see, it rotates, but okay, how do we understand this? How a system of particles like prepared in this 0-degree configuration can spontaneously rotate into 45-degree configuration. In order to understand this, let's look at the more microscopic details of the system. In particular, here on the right, you see quantum thermal densities of the particles. What I mean by this is the following. So these particles are described by wave functions. So they have their quantum properties preserved, and they are basically thermal. So you can think of this as they are at very low temperature, or the sizes are very small, so that they show their wave nature. And you can see that this is how at thermal equilibrium these particles will, where these particles occupy. So zero occupation on the near to boundaries. This is not surprising because remember the Dirichlet boundary condition we imposed. And there are more occupation probability on the less confined parts of the domain. But this changes when you allow to rotate this inner object. As you can see, for example, let's check the 25-degree configuration. There are more particles here on this side to collide with the walls. By collide, don't necessarily think of a collision of a point particle, but the pressure of the wave that is exposed into this domain. So we can check how the pressure distribution varies in this alongside this wall, and we find this. As expected, the pressure distribution is basically asymmetric. It's non-uniform. And remember, so this is symmetric in 4 cases. So particles provide more pressure onto these sides of the walls and make this thing rotate. So this is a microscopic justification of the non-uniform pressure distribution. And this is more of a global perspective. We can calculate torque from free energy. As you can see, it starts at 0 configuration. The torque is 0. Well, this is understandable because the system is symmetric. Particles exert pressure the same way to all walls, all the parts of the walls. But if you give an initial perturbation to the 0-degree configuration, you will realize that there is a finite amount of torque and it will rotate spontaneously. So this is something quite interesting.
Alhun,
yeah.
I'm stopping. I'm sorry. You're kind of over your time, but since there were some questions, we will have maybe up till 40 past. All right. So 7 more minutes.
Okay. I
won't disturb you anymore.
Okay. Thank you. Okay. Let me also show you this slide, which is quite important because I mentioned the decrease in entropy. So let's construct a heat engine based on this quantum shape effect, this size-invariant shape transformation. So let's prepare a domain like at this configuration, 45 degree at 200 Kelvin. So we perform an isoformal process, which means shape preserving process. So we don't touch to the shape of the domain, we don't rotate it, just we give heat. And its temperature raises to 300 Kelvin. At this point, we are rotating the 45 degree, the inner object to 0-degree configuration. By doing this, we are applying work on the system, and also we have to give heat to the system, which is very surprising because in classical cycles, when you apply force, there is heat rejection from the system. But here, the signs are flipped, and this is exactly due to the behavior of this entropy. Okay, then we, under isoformal process, we cool down the system and we complete the cycle with another isothermal process by allowing the system to rotate itself, and we can extract work from it and also heat. So this is how TS and tau theta diagrams look like. Remember, in the isochoric process, we will have PDV, pressure volume diagram. So here we have tau theta diagram, and you can see that the amount of work that you can get from the cold side is larger than the amount of work you put on the hot side. So again, compared to classical thermodynamic cycles, this behavior is reversed. You take the work from the system at the hot side in the classical systems. But here it is reversed. So this is also interesting. Another thing which is quite related to these things, you don't see here, but it's basically this, all of this means that you can effectively compress your system and the temperature will drop during this compression, effective compression. So it is completely against the ideal gas law here. So this is quite interesting. You can basically cool things down by compressing them. Of course, I'm talking about an effective compression here, not in terms of like changing the sizes. Okay, there's another thing which we did in terms of an application of this thing, which is thermoshape effect. I will just briefly mention this. This is basically a thermoelectric-like effect where the thermoelectric voltage is based on the temperature difference, but also shape difference. So instead of using PN junction, for example, different materials, you can use the same material but having different shapes, but the same sizes. You can still have, you can generate a voltage from this. So this is one way to demonstrate and take advantage from these kind of systems. If you like this thing, there are many things to be done, and if you want to read more about it, I can refer you to my thesis, which is in archive. And last thing I would like to mention is Blockbusters, which is educational science and art website that we constructed with our Harvard colleagues, and we are presenting this beautiful looking, artistic looking images and explaining the physics behind them. So I will be glad if you take a look at this. Thank you very much for your attention.
Thank you for this nice talk, Alhun. Unfortunately, I had to I had some internet connection errors and I couldn't follow some part, but we are ready to take some questions. If not, I'll keep on going with my trivial questions. Seems Victor has one. Please,
Well,
Victor.
I mean, I don't know to what extent this is like, so why exactly did you say that the entropy was dropping then? Like, what's the physical intuitive reason for the entropy drop?
So it is quite subtle. There are several explanations I can provide for this entropy drop. So in my thesis, since I haven't mentioned this here, but we actually proposed an analytical method to predict these quantum shape effects. And there I can write the expression for entropy, where I can see that there are additional terms to entropy, which are coming from basically this shape variation. So entropy is a function of theta, and you can see exactly how this term looks like, which is about, so the reason of this entropy decrease from that perspective is it is a complicated function of shape, but it's a vague words. I can say also this. So there is this effective volume emerging under this this transformation. I can show you how it looks like. So at least give it some sense. So effective volume is this area which are not covered by blue, where there are no particles. So this effective area actually changes during this. And this effective area is temperature dependent. So this additional temperature dependence actually is the main cause of this decrease in entropy. So in a sense, your heat term involves temperature dependence. So there are correlations between work and heat in your system, which are coming from this description. So in that sense, there's one explanation for the decrease from this side, but more fundamentally, what is happening is quite related to this. Let me show you that. Okay, so here I mentioned that there is this reduction of entropy. So basically, entropy is about the distribution of the states in your energy levels. So the populations of the states are important. That characterizes the behavior of entropy. So from 0 to 45-degree configuration, you can see that ground state decreases a lot. This makes ground state population to increase a lot. So this is basically accumulation of the particles into ground state, which has less entropy. So this is the fundamental reason why entropy decreases. This is different from the size effects, because in size effects, the spectrum is populated like regularly. Like if you increase the sizes, ground state population will be increased, but also the other low-lying and high-lying states are also populated. Here, there's this weird mixture of this population which causes this behavior.
Thank you. I think Tekinoja has another question. Right?
Yes, can I just shortly comment? Well, you talked about this talk, and also you talked about perturbing the system. Then I thought, well, the configuration that you have started with, you have a square and then you carve a smaller square out of it. The picture is symmetric, right?
Yes.
And then in the second and the third and the fourth diagrams, these are asymmetric. So is there any problem with stability?
You mean asymmetric in this here? In the
well, I mean, we have a well, you have this fourfold symmetry in the first diagram, but you don't have that in the second diagram.
Oh, but fourfold symmetry is preserved under this rotation.
But I mean, if you rotate this square as a whole, but I'm talking about the rotation of the inner square.
Yeah. But rotation of the inner square, if you, for example,
the first, your starting initial configuration is symmetric, your second configuration is not symmetric.
Oh, this is also symmetric. So
Well, it's not the same symmetry though. If you look at the final configuration, the symmetries are different.
Tekin Hocam, look at this way. So follow this
way.
y and x axes, which are also rotating. And look at this first quadrant here. So this first quadrant is exactly the same with the other quadrants. You can replace them as you like. It's just rotated version of each other. So in that sense, the axial symmetry is preserved. It is easier for the 45-degree configuration. If you look at this,
but where does the torque come from?
Sorry?
Where does the torque come from?
Torque is not coming from this breaking of global shape symmetry. Torque is coming from how particles occupy different parts of the domain. So if you look locally in this quadrant, for example, you will see that particles now occupy much more space in here rather than here. So this means there is more torque in this direction compared to the middle part.
So does this torque tend to bring the configuration back, or will it rotate it further?
No, so it will rotate to the 45-degree configuration and stay there because that's the minimum free energy configuration. It is symmetric in terms of, okay, there are two symmetries. So the global symmetry is preserved, as I said. If you look at axial symmetry, but there's a symmetry breaking here in the local distributions of this particles.
So
that determines.
So this stable configuration is the last one.
Stable configuration is the 45-degree one.
Okay, that's what I'm asking. Okay. Well, I'm okay. We can talk about it later privately, perhaps. But if I have time, can I ask also about the Weyl conjecture? When you say it's a conjecture, then it's not derived. It's not a theorem. It's not proven. It's a conjecture, but it's quite intricate. You have the gamma function. You have the square root of pi. Is there any intuitive way how this conjecture comes about? It's not very intuitive.
Can I also ask an additional question? Because the second one that you gave us in the Weyl conjectures, it awful lot looks like the Euler characteristic of the shape that you started with, although there are a little bit differences.
Yeah, definitely there are connections. So I will explore some of these connections in the paper that I'm writing right now. So if you're interested, I will send it soon, hopefully.
Okay.
So about Weyl conjecture, so it's kind of semantics here. Some people call it Weyl law because it is actually proved for special cases that this is the case. But there are some other special cases which are not really proved. So some people prefer it to say Weyl law, some people say Weyl conjecture. So it depends on your preference, just for that conjecture word that I can say. So about the form of this, so I put this into this form because it looks very, intuitively appealing in terms of, like, you see volume here, and this is, so this gamma function and so on, they are basically coming from the formula, the expression for n-dimensional volume.
Okay, normalization factors.
Exactly, those normalization factors are directly related to the n-volume formula. If you open these two formulas, you will see that connection immediately. And so I put it this form. This is a bit like a closed form because it involves also many terms here. Like it has like for example, 3 terms generated by this sum here. So it's not actually a summation basically, because I just wanted to make it like n-dimensional, like general form. But yeah, so this is directly related to the n-dimensional volume.
Okay, thank you. So at least for some special cases, it's right.
Yeah. And if you check numerically, you will build much more confidence and trust to this formula because it is really. There are cases, for example, it could not violate, but it could give some bad results, especially in the low end of the spectrum, the lower lying eigenvalues. For example, if your domain is very anisometric, like you have a circle here, but there is this thin line going to the left, for example. So this is these kind of domains, Weyl law might seem to fail at first, but since this is an asymptotic behavior, it should give the same behavior in the infinity.
Yeah, okay, thank you, thank you. This is a very nice talk.
Thank you. I'm glad you liked it.
Okay, since I am the chair, I will ask my own questions because you guys asked a lot of questions and I will not stop myself. So I have two questions about shapes, actually. The first one is this, just for fun. If you give me two different shapes, can their spectra be the same? And the second, I think this is a very hard question to tackle, but I may have read something about it somewhere. Maybe you told it when I was gone. I'm sorry.
Yeah. I mentioned that they are called isospectral domains.
Oh, that's what it was. Okay, thank you. Okay, now
here.
Yeah, I was not here. My bad. Quite bad.
No,
Sorry.
okay. So I also lost the connection there. Maybe that's why you missed. But these two domains are basically having the same sizes, different shape, but their eigenspectrum is exactly identical.
Quite nice. The second one is this. I would like to do some engineering applications using these, like build up some sort of motors, maybe something like that. Which shape would you suggest me to use? Because I think that should be a good practical question that people should answer in working for building, who wants to build technologies using these, right?
Yeah, that's a very good question. I think we can tell some things about that because, okay, it depends on what you want. What is the application?
Most efficient one. I want to milk it as much as I can. It's a machine and I want to make it as much efficient as I can. As a motor, say.
As a motor?
Yeah. I want to build a motor, a quantum motor, whatever you want to call it, fill it with gas, do some shape transformation.
For example, here, this is very related to what you say. So I didn't hear mention the efficiency.
Yes.
Here, but as far as I remember, it was something like 25% was the energy conversion efficiency in this particular cycle.
Compared to a Carnot with these temperatures?
Compared to Carnot, it's low, of course.
Yeah, but how low?
Yeah, okay. Let me try to remember. I guess Carnot was 66, something like that.
Okay, that's a lot lower than.
Yeah, it's not very close to Carnot in that sense.
Okay.
I would claim it is very efficient.
Yeah.
But it depends very much on your initial configuration. So it is basically how you construct your system, like the particular shape you choose. For example, here we see nested squares. You could do anything you want, like Tekino just suggested. It might be like something with different holes in it. So from the efficiency perspective, in order to maximize these effects, what I can suggest is make the boundaries closer to each other, as close as possible. Because we explained this, I didn't have time to explain that part in this talk, but there is direct connection which we built analytically, that the overlaps of quantum boundary layers determine this shape difference. And closer the boundaries, this inner and outer boundaries that I'm talking about, closer them to each other, more shape effect you have.
Okay, thank you so much, Alhun.
You said that you have also treated triangular shapes, right? Before?
Yes.
Why don't you construct a quantum Wankel engine? Do you know that?
Oh yeah, I know. That's a good suggestion, actually. Yeah, I was.
Oh, Wankel engine.
Yeah, Wankel engine. So it's. I was thinking about that during my PhD. Then I actually tried to like make it realized by reading some more about the engineering part of it. Then I realized that wait, this is going too much to the engineering perspective. There are many things I need to consider which I don't really know. Then I stopped, but of course, I mean that's a good suggestion. It can be done.
A square Wankel engine, quantum square Wankel engine. Why not?
Yeah, that's what we can do. Anything exactly. Yeah.
Okay, so if there are no other questions, and since I officially do not have any other questions for now, we have the afternoon meeting now. I guess we will come back in like 17 minutes because we do not want to push the schedule further. Okay, so we will meet Istanbul time 5:10 as scheduled before with your ghost talk. All right, so I'll see you guys soon.
Thank you. See you. Bye.
Yep.
See you. Thank you, Alhun.
Thank
Yes,
you.
thank you, Alhun, again.
Thank you for listening.